There is a quiet assumption at the foundation of science that the world behaves in ways that can be measured, repeated, and understood. Not always immediately, but eventually. Patterns emerge, causes reveal themselves, unknowns become known, and over time, uncertainty is reduced, but not eliminated. There are moments, small, infrequent, and often overlooked, where observation does not settle into explanation, where something is recorded clearly, objectively, yet remains unresolved. Not because it is hidden, but because it does not behave as expected. In the late 19th century, a scientist studying light noticed something unusual. It was not dramatic, not disruptive, just inconsistent. The measurements were precise, the instruments were reliable, and yet, the results did not align with the established understanding of physics. At first, it was assumed to be error, but the inconsistency remained. Quietly, repeatedly, and over time, it began to raise a subtle question. What happens when something is observed but cannot be explained within the limits of existing knowledge? In the year 1887, in Cleveland, Ohio, two physicists, Albert A. Michelson and Edward W. Morley, conducted an experiment. Their goal was precise and grounded in the physics of the time. They were attempting to detect the presence of something known as the luminiferous ether. At the time, this concept was widely accepted. Light, it was believed, needed a medium to travel through. Just as sound moves through air, light was thought to move through an invisible substance that filled all of space. This ether, though undetectable directly, was assumed to exist, and if it existed, it should produce measurable effects. The Earth moves through space, and if space is filled with ether, then the Earth should be moving through that medium. This motion should create a detectable difference in the speed of light depending on direction. Michelson and Morley designed an experiment to measure exactly that. They used an interferometer, a device capable of detecting extremely small differences in the speed of light. Light beams were split, sent in perpendicular directions, and then recombined. If the ether existed, there should be a shift in the interference pattern, a small one, but measurable. The experiment was conducted carefully, repeatedly, under controlled conditions, and the result was nothing. No shift, no detectable difference, no evidence of the ether. The measurement was not unclear, it was precise, consistently precise, and consistently, it showed no effect. This result was unexpected, not because it was dramatic, but because it contradicted a deeply held assumption. If light did not require a medium, then what was it traveling through? And more importantly, why did the experiment show no variation at all? Was the ether simply undetectable, or did it not exist? In the years that followed, scientists attempted to reconcile this result with existing theory. One possibility was error. Perhaps the instruments were not sensitive enough. Perhaps environmental conditions interfered with the measurements, but repeated experiments, with increasing precision, produced the same outcome. No ether wind, no directional difference. Another idea emerged. What if the ether existed, but behaved in a way that prevented detection? This led to complex hypotheses. One such explanation suggested that objects moving through the ether might contract slightly in the direction of motion. This contraction would offset the expected differences in light speed, making the ether effectively invisible to measurement. This concept later known as Lorentz contraction, was mathematically consistent, but it raised further questions. Why would physical objects change length just to preserve the appearance of an undetectable medium? The explanation felt constructed, functional, but not satisfying. Then, in the early 20th century, a different approach emerged. Instead of trying to preserve the concept of ether, what if the assumption itself was incorrect? What if light did not require a medium at all? This idea would eventually lead to a fundamental shift in physics, but at the time, it was not immediately accepted, because it required abandoning a long-standing framework and replacing it with something not yet fully understood. Even as new theories developed, the implications of the original experiment remained complex. The absence of ether was not simply a missing substance. It implied something deeper about space, about motion, about measurement itself. If the speed of light was constant, regardless of direction, then motion was not behaving as expected. Time might not be absolute. Space might not be fixed. These ideas were difficult to accept, not because they lacked evidence, but because they conflicted with intuition. And even as theoretical frameworks began to accommodate these ideas, questions remained. Why does light behave this way? Why is its speed constant? What defines the structure of space itself? The Michelson-Morley experiment did not answer these questions. It revealed them. And in doing so, it marked a boundary, not of knowledge gained, but of assumptions that could no longer hold. Nearly a century later, in the late 20th century, another set of observations began to challenge understanding, this time not in a laboratory, but in the vastness of space. Astronomers studying distant galaxies noticed something unusual. Galaxies rotate. Stars orbit their centers just as planets orbit a star. Based on observable mass, the speed of these stars should decrease with distance from the center. This is what gravitational theory predicts, and it is what we observe in smaller systems. But when astronomers measured the rotation of galaxies, they found something different. The outer stars, far from the center, were moving much faster than expected. Not slightly faster, but significantly so. According to known physics, these stars should not remain bound to the galaxy. They should drift away, and yet they did not. The measurements were repeated across different galaxies, different regions of space, different observational methods, and the pattern remained consistent, persistent, unexplained. To account for this discrepancy, scientists proposed a new concept, dark matter, an unseen form of mass that does not emit light, but exerts gravitational influence. If galaxies contained large amounts of this invisible matter, the observed rotation speeds could be explained. Mathematically, it worked, but observationally, dark matter has never been directly detected. Its existence is inferred, not observed, and despite decades of research, its nature remains unknown. These two phenomena, separated by time and scale, share a common structure, an observation that does not align with expectation, a measurement that resists explanation. In both cases, science responds not with certainty, but with adaptation. New theories are proposed, new models are constructed, and in doing so, the boundaries of understanding are extended, but not eliminated, because each solution introduces new unknowns. If the ether does not exist, what defines the structure of space? If dark matter exists, what is it made of? How does it interact with the known universe? These questions are not failures. They are indicators, markers of where knowledge currently ends and where exploration. When faced with unresolved phenomena, the human mind responds in specific ways. We look for patterns, we construct narratives, we attempt to complete incomplete information. This is not a flaw, it is a function. Pattern recognition is essential for survival. But it can also lead to assumptions. When data is incomplete, the mind fills gaps, sometimes accurately, sometimes not. In the case of scientific mysteries, this tendency can influence interpretation. Ambiguity becomes meaning. Uncertainty becomes explanation. But science, as a process, attempts to resist this. It holds observation separate from conclusion. It allows uncertainty to remain, not indefinitely, but until sufficient evidence emerges. This restraint is what distinguishes scientific inquiry from speculation. And yet, it also means that some questions remain open. There is a quiet boundary in all systems of knowledge, a point at which explanation becomes approximation, and beyond that, uncertainty, not because the universe is unknowable, but because our tools are limited, our measurements are finite, our models are constructed, and while they improve, they are never complete. The absence of ether did not simplify physics, it transformed it. The concept of dark matter does not resolve observation, it extends it. Each discovery reveals structure, but also reveals absence, gaps where explanation has not yet reached. And perhaps this is not a temporary condition, but a fundamental aspect of understanding. That knowledge expands, but never closes entirely. There are observations that remain, carefully recorded, repeatedly measured, and still not fully explained. They do not disrupt science, they define its edge, a place where certainty fades and inquiry continues, not with urgency, but with patience. So the question remains, not whether these phenomena will be explained, but what their existence already tells us about the limits of measurement, about the structure of reality, and about the nature of understanding itself. Is this simply a matter of time before clarity emerges, or are some patterns meant to remain incomplete within the scope of what we can observe? If you've followed this far, you may already have your own interpretation. So, what do you think? Are these mysteries temporary gaps in knowledge, or reflections of deeper limits we are only beginning to recognize? And if you find yourself drawn to questions like these, quietly unresolved, consider subscribing for more explorations at the edge of understanding.